first acknowledge the Aboriginal and Torres Strait Islander traditional custodians of the land on which we work and learn, and pay respect to their elders, past, present, and emerging, and acknowledge the place of Indigenous knowledge in the Academy. Welcome to today's seminar of the Melbourne Mathematics, Science and Technology Education Group of the University of Melbourne. My name is Jan van Driel, and I'm together with Professor Wee Cheong leading the Math, Science and Technology Education Group. And I will introduce our speaker for today, Professor Jonathan Osborne, in a minute. But before I do that, I'll just briefly give you a sense of how the seminar will be run. Once I've had an opportunity to introduce Professor Osborne, he will give a talk of about 40 minutes and share his screen with a presentation for that purpose. After that, we will have a Q&A session until it's 6 o'clock here in Melbourne. The Q&A will be moderated by Dr. Emily Rochette, and you are all invited to put your questions, comments, or what have you in the chat, and that you can do that during the lecture as well as, of course, after Jonathan has finished his presentation, and you can, and then Emily will feed the questions to Jonathan to talk about, and we will finish at 6 o'clock sharp here in Melbourne time. So it is my great pleasure and privilege to introduce today's speaker, Professor Jonathan Osborne. He's currently in Berlin, where it is 8 a.m. in the morning. So thank you, Jonathan, for being with us at this early time of the day. Jonathan is one of the most prolific researchers in science education and has been in the last 20 plus years. And I could take too much of his time by talking about all the accolades that he has achieved in his career. I will only briefly highlight a few things. In 2000, Jonathan became Professor of Science Education at King's College in London. And in 2003, he became the Chair of Science Education at the same place. A few years later, he was president of NAST in 2006 and 7, and then he moved in 2009 to Stanford University, where he has since been the Kamalachari Chair in Science Education. Currently, Jonathan is the chair of the OECD PISA Science Expert Group since 2018, and in that capacity, he will actually visit Melbourne in February of next year. Most of us, at least the people who work in science education, will be aware of at least two strands of work that Jonathan has been not only very productive in, but also, I think, very impactful in. One is the role of scientific argumentation in classrooms and the pedagogy, the teaching of scientific argumentation by teachers. He's done a lot of projects in that domain and published papers, some of which have been cited very, very many times. And he's currently doing a project together with Mark Wilson of University of California in Berkeley, who's also affiliated with the University of Melbourne, on to establish a learning progression for argumentation. The other main strand in Jonathan's work is related to making science education more worthwhile, more engaging for students. In that line of work, he's published a paper that many of you will know about attitudes towards science, which was published in 2003, I think, and has been cited like almost 5,000 times if you look it up on Google Scholar, as I did today. So that's an incredible, impactful paper. But related to that, he's also written reports about science education in Europe, a report to which I made a minor contribution. And I do remember very well the meetings that we had in London to produce that report. And before that, there was a report with Robin Miller about Beyond 2000, reports that are about science education as it is, but looking to the future of what science education should be to prepare not only those people who want to become scientists, but certainly also the people who, like the broader audience, who to become more science literate, if you want to use that phrase. And in that same strand of work, I think I see the report that came out a couple of months ago called Science Education in an Age of Misinformation, of which Jonathan is the lead author. And I think this is a good moment for me to hand over to Jonathan to start talking about that report and once again, I'm very grateful and happy that you are available and willing to share your insights with us today. Thank you so much.
Thanks very much, Jan, for that far too generous introduction. Thank you for coming to listen to me. I'm just going to share my screen. Hopefully this is all going to work. We did try it out beforehand. And you should be seeing my slides now. Is that correct? You're seeing my slides, right? Okay. As Jan said, I'm here to talk about this report, Science Education in an Age of Misinformation, and really give you a kind of overview of why we produced it, why we think it's important, and what the implications and consequences are. And please, as I'm talking along and you have questions, do sort of post them in the chat. I can't actually see the chat at the moment, but I will, as soon as we finish, I'll look there and go through the questions or post them to Emily, who I think is moderating it. Okay, so let me start with why, in some senses. This, by the way, is the report. If you haven't got a copy of it, it's available from that website. And there are other bits and resources that come from the website as well. Originally, we had a kind of argument in the group as to whether we should call it science education in a post-truth society, but this is what it ended up being in that way. So the question is why, and this wasn't, I think, particularly high on my agenda in the sense that there are other things. I'm technically retired now, so you don't go looking for work, but I was approached by Bruce Alberts and Janet Coffey, who are very concerned about the rise in scientific misinformation associated with the pandemic, but also I think going back, there is increasingly a sense in which people find or challenge some of what you might call consensually agreed science in that way. And there has been a fundamental change, I think, in the nature of the society we live in the way in which information is transmitted. And that's happened really with the advent of the Web 2.0 and the internet and the way in which people can communicate misinformation. And yes, misinformation has always been around. There have always been the snake oil salesmen in that way, but the internet has given them two things. It's given them a much larger megaphone. And secondly, there are clearly no gatekeepers whatsoever most of the time on the internet. So it leads to what you might call a plethora of information, some of which is sound, some of which is totally ridiculous, like COVID-19 is caused by 5G wireless networks. And yet people don't have what you might call the knowledge or the capacity to evaluate that information itself. And that's a challenge. And it's a challenge which science education needs to think about how it can actually address. And this challenge, I think, has been documented in various writings. It's been an interesting education for me working on this report, reading all these books. If you haven't read them, these are two. I particularly recommend The Death of Expertise, which is a highly readable book from that point of view. And what Nichols points to in that book is the way in which people think that they don't need experts, that the internet somehow has given them this sense of being independent of experts. And I think the fundamental tenet, which I'll elaborate of our report, is that actually we're living in a society where we are ever more dependent on experts because we know a lot about a little. And to know anything about other areas of domains, we have to make judgments of trust and credibility. And we have to educate people that that's the situation that they're in. So there needs to be some sort of education for intellectual humility. And we need to educate them how to approach making judgments in a context where they don't have relevant expertise. This is another book documenting this concern. I mean, a lot of it's arisen, obviously, since 2016 with the willingness of people to believe things that are basically fundamentally, there is no evidence whatsoever for. I mean, the obvious one is the idea that the American elections were stolen, which is perpetrated by Donald Trump. But there are many more, I'm sure, that you can think of. And this generates a concern because I think if you occupy a kind of epistemic position that values knowledge which is based on evidence, which I think is to some extent, or to a large extent, what science is, the fact that people choose to reject evidence is a concern, because then you're living in a society where how do you establish any sense of truth? And that's really, I think, what this book is about. And one characterization, kind of amusing characterization of this, again, is the four horsemen of the apocalypse: war, famine, pestilence, death, and then the arrival of a new one, the fifth, misinformation. And I think that's the kind of background to this concern that people had. And so we thought, well, what we'll do, this is something we need to discuss, what the contribution of science education can be. So we'll gather together a group of people. It's all done online in that sense, funded by the Moore Foundation. And you can see who some of those people are. They're Bruce Alberts, Doug Zolchin, who's written on these issues. Sarah Barsley has written, again, on this from a science education perspective. Carl Bergstrom has written a book called Calling Bullshit. Brian Donovan is somebody who I know who works in science education. Rena Dorf is the director of Lawrence Hall of Science. Kari Kivenen works for FACT-BARI Finland and has done lots of work in Europe on this issue. Anastasia Kozreva is somebody who works at the Max Planck Institute. And so there are a mix of scientists. Saul Perlmutter, for instance, is a scientist. He's actually a Nobel Prize winner. And Sam Weinberg, who's, if you haven't come across his work, is a history educator. He's a colleague of mine, and he has done a lot of this work on this and what you can do. So this is the report is the kind of distilled wisdom. I mean, I may be the lead author, but it's really the distilled wisdom of this group of people who have been through it several times and shredded it. And their input is of these. Some of these. I'll just give you a sample of some of it. Douglas Zolchin wrote a paper on reconceptualizing nature of science education in the age of social media, and I think Douglas Zolchin has thought quite a lot about this. Sarah Barsley with Clark Chin on education for a post-truth world. And then Anastasia Kozreva, a long paper, but a very worthwhile paper on citizens versus the internet, confronting digital challenges with cognitive tools, with Stefan Lewandowski, who's, again, one of the people who's written quite a lot about this. So we are fundamentally what you might call a bunch of academics looking at this. What's missing, I think, in some senses, is a teacher voice, but I'll talk a little bit more. But we have made presentations to teachers, and I'm happy to talk about how they react to what we're doing. So this report starts from a premise, essentially, that true knowledge is a collective good in that kind of way. And that's really what, in some senses, the goal of this work is, which is to enable people to, or give them the skills, competencies, knowledge in order to decide what is true, because true knowledge is incredibly important in that sense. So an example of that obviously being the role of vaccines in mitigating, diminishing, preventing you getting ill with COVID-19. And when people perpetrate arguments, for instance, that vaccines are ineffective, then it has severe costs. And in the case of America, there is good data which shows that Republicans who have chosen to deny the role of vaccines on an issue of politics or identity have died in much larger numbers than Democrats. And that matters. And that's just one example. And I'm sure you can think of many other examples where it matters. And at the heart of the report is really the answer to this question, and how you answer it and think about how you came to know your answer you have. And the question is climate change an anthropogenic effect? Now, if we were all gathered together, I would ask you to put your hands up as to whether you believe that. And I'm going to make an inference that you all do, or at least 99% of you do. So then my question to you would be, why? Because how many of you have read the IPCC report? Now, apart from Peter, who I saw there, I think an answer is probably very few. So the question is, why do you believe it? And the answer, if you explore it in discussion, I could ask you to discuss it with the person next to you, would be probably because you know it's a consensus report, it's a consensus of experts, you have faith in experts, and therefore you believe what they write, or you've read about it in some media source which you regard as being trustworthy in that way. And if you go one step further, you might have seen the attempts at counter-arguments and think they're a bit facile from that point of view. So fundamentally, we believe things because we have trust in people who are experts. And that's really true of so much of our daily life. We depend on experts. You depend on experts to run the traffic systems in your city. You depend on experts to maintain your health. You depend on experts to fix your cars. You depend on experts if you need legal advice in that kind of way. And so the question is, how do we develop a healthy relationship with expertise? And in the case of science, the argument I'm going to make is that much science education is based on what I call the Deweyan delusion, that it's possible to educate people with sufficient knowledge to be intellectually independent to evaluate the arguments for themselves. And I'm sorry, but that is not true. And it's flawed. I could not evaluate the arguments in the IPCC report and the evidence on which it's based. And if I can't do it, then I'm pretty sure the average 15-year-old can't do it as well. Now, don't get me wrong about the internet, and I'm sure most of us think it's a wonderful thing. You know, if you want useful information, we're all resorting to it every day in order to get it. But note, the word I'm using is information, not knowledge. And I'll try and draw a distinction between knowledge and information. And you can get answers to all these kinds of questions. And if you've got something broken or you need to do it quickly, you can easily find the answer to these kinds of questions. But there's also misinformation out there, people making arguments for things that actually are for which there is no evidence. These are just some of them in that kind of way. You wonder sometimes why they're doing it. Some of it's sometimes an ideological commitment or a religious commitment. I was talking to somebody yesterday who was talking about, he'd been to a talk somewhere in the Midwest where they were arguing that dinosaurs existed with humans. This is fundamental. They need to argue this in order to believe in the literal account of the Bible. And they will be, the interesting thing about their arguments in some senses is they, in some senses, are on the back foot because they know what you might call the epistemic supremacy of science. So they know they have to produce evidence. Of course, the evidence they produce is odd little bits of things like footprints of a footprint of a human which is found above a tribalite somewhere in the Midwest. Well, there are all kinds of ways that could come to be. So there's misinformation out there, and then there's just simply what you might call malinformation, where people are actually promoting things that are fundamentally wrong, because anybody who looks up, is there a scientific consensus on climate change on Google will find a very clear answer that there is in that way. So this is the context in which we're operating. And that then really drove us to say, well, these are our 4 questions which are driving the report. Why do students need the ability to evaluate expertise and information? What evidence is there that young people struggle to evaluate successfully? After all, a lot of people think, look, they're growing up in this kind of milieu of information. Surely they won't have any problems. It's just you and me, the old people, who have problems. Why is it an urgent priority for scientists and science educators to develop students' competency to evaluate information? And I'll try and answer that as best I can. And then what can we do to develop the competency to evaluate that information? So those are the 4 questions that I'm attempting to run through. And let's run through them one by one. Get that to go. Sorry, it's got stuck for some reason. Why has it got stuck? Oh, there we are. Oh. Okay, sorry, it's just being slow. I go back. Okay. Right. I think that's all right. Just check. Sorry. Yeah. Okay, right slide. As I pointed out, I think the internet, you may not think so, but the internet is a novel information environment. It has had a big effect on the societies in which we live, in the ways in which we communicate, the ways in which we get information. And just as we were talking about beforehand, it enables us to come together in ways that were not possible beforehand. However, as I said, there are very few gatekeepers to that information that you get on the internet. You are then forced into the position of making judgments about the quality of information you get. It's not like going to a newspaper where you know certain things only get printed because somebody selected it and it's been reviewed. So how do you decide? And then I'm afraid, and people don't like this, students are poor at evaluating sources. That's what all the research evidence shows. And this is a sample of a piece of work from my colleague Sam Weinberg, and there's much more than this, but as he says, as researchers have shown, such claims persist despite a 2019 national survey of 3,446 high school students that revealed major deficiencies in evaluating the credibility of online sources. 52% said that a Facebook video claiming to show ballot stuffing during the 2016 Democratic primary elections, a video that came from Russia, a fact easily established by searching for 2016 voter fraud video, constituted strong evidence of US voter fraud. And that, I think, is really concerning, that people, when you see something which in some senses is instinctively against what you might call one's rational beliefs, that actually American elections are not are susceptible to fraud, that people don't go looking for the fraud explanation in that way. And 9 out of 10 students were unable to come up with a cogent rationale for rejecting the video. So that's just one sample, but there are many more samples. So the point is, no, students, when it comes to this, are digital novices, or they're digitally naive. And that's just because they are young people, and they haven't yet been, the skill of doing this hasn't been developed, and it's not something that's been attended to by education. Another problem with them is that they think .org is an indicator of a reputable website. Now, I'm afraid .org is not an indicator of a reputable website. This is a very irreputable website, 9111truth.org. It promotes conspiracy theories about 9111 Truth. But what it does, okay, is do something which is very common to all of these websites. It says it appeals to the sense that you are intellectually independent. Circled up in the red at the top there, it says, think for yourself, explore the facts. Now, the facts have been cherry-picked. And nobody really has the knowledge, in some senses, to identify that unless you happen to be an expert and you know what the expert arguments are. Probably in this case you might do because they're so blatantly flawed, but you cannot think for yourself. The first thing you have to do is make a judgment about who is promoting this and who is the person who is making this claim in that way. And then I think this is the point I made earlier on, and this is fundamental, I think, to our thinking about the role of science education. Most of us use reputation as the basis of epistemic trust when it comes to selecting anybody like a plumber, a lawyer, or whatever it is. You can't do that with a scientist because, we don't have many scientists who are scientific experts or friends, and even if we did, it happened to be a cosmologist when actually what you want is advice about evolutionary biology or whatever it is. So from that point of view, you are forced, in the case of scientific experts, into making judgments about whether they have qualified expertise in the domain in which they are making claims. And the question then is, what knowledge do you need in order to do that at least reasonably well? And then fundamentally, this is the point which we are all epistemically dependent, and we are increasingly epistemically dependent on the expertise of others. Every time I go through an airport, for instance, you look at the sophisticated systems that keep that whole system running, and you realize that you're very dependent on a lot of experts in that way. So what are the implications for science education? As I said, students may be digital natives, but they're also digital novices issues. The key issue is, who do you trust and how do you educate people that? And what are the criteria of trust and credibility? But fundamentally, I think it requires a shift in our thinking. Now, I don't know about you, and I can't speak for the Australian curriculum, but most curriculum pay lip service to the notion of educating people for scientific literacy. It's used as a rationale to justify why we educate everybody in science. Now, the reality is that actually my somewhat jaundiced views at my age is that actually that's a fig leaf to cover up the fact that most people are being forced to do science for the 5% who will go on and become scientists. And if you push it, they'll say, well, we all depend upon those 5%. We don't know which 5% it is, so we've got to do it to everybody. And in the course of doing it to everybody, of course, you kill any kind of enthusiasm for the majority. That's a very jaundiced view, I'm afraid, of it. And when you ask, well, what about this stuff for educating for scientific literacy? Oh, well, they're going to pick up a bit of knowledge that'll help them work out some of the stuff that they need to deal with in life. And the reality is, no, they're not going to pick up any kind of coherent framework. You've got to think about educating them to become competent outsiders. This is a phrase drawn from the work of Einstein, because that's what we all are. We are outsiders to expertise. How do we make good judgments about expertise in that way? And that has to be a central feature of what we are doing, and that requires a rethinking. Now, to give you a good example of this, the failure of operationalizing this. I was involved in writing the framework for K-12 science education, which then became the next generation science standards in the US. In that framework, again, it was almost ashamed to admit it, but I think there are a few mentions as rationales in terms of scientific literacy and educating people for scientific literacy. When you come to look at the performance expectations in NJSS, there is really not one which is some kind of measure of students to evaluate scientific information. That's despite the fact that there is a practice 8, which is about communicating, obtaining, and evaluating information. All of it really is focused on what you might call the basics, life sciences, earth sciences, and conceptual knowledge. And that is something that has to be rethought. Okay, so in putting this together, the answers to what needs to be done, this is some of the kind of work we've drawn on. Carl Bergstrom, his book, Calling Bullshit, very good read. He has a website. Sam Weinberg's work on civic online reasoning also has a website, and there's some science resources there. And then Fat Barry, who educate, this is a curriculum initiative in Finland. They educate students from the age of 8 upwards in some of these competencies, and it's fundamental in that way. You're also drawing on these kinds of thinking. Again, these are all very interesting books to read. Andrew Jewett's documenting of how science has come under fire. In fact, science has been under fire for a long period of time, if you think about it. People don't like some of the things that science has to say. Gloria Ricci's work on reputation and how that is used as the basis of trust, and that's, again, and Steven Pinker's work on rationality. But there are many other things that come across it, but it's been an interesting journey. So what can be done? And this, in some senses, the report, I think, offers a kind of basic, simplistic approach, saying that there are really 2 things that need to be done. One of them is general, and the other 2, or the other aspects of it, are specific to science. And science has to step up to the plate to do them, because you can't expect civics to do it, because that's one of the responses that people have. They say, oh, well, yeah, I understand this is a problem, but why do we have to do it in science education? Can't they do it in civics? Well, this bit could, for instance, be done in civics, but anyway, no. But I think you only acquire these habits if you practice them regularly. And this is Sam Weinberg's work, studied expert fact checkers. What do? And really, they do two fundamental things whenever they're confronted with a claim or a web page on the internet. First of all, if they've got a question, they use click restraint. They put the question in, and you know what it is in Google. You get, these days, I don't know about you, but I get all the ads. So you ignore the ads, and then you go down, and then you've got to choose one to pick. So they are much slower about picking one. They look at all of these choices that Google's giving you. And I don't know whether many, I wasn't aware of it, but you may not be aware of it, but if you look at Google these days, beside each of the results, there's 3 little dots. And if you press on the dots, it gives you information about the source. So that's something they use as well. And then they pick one and they open the web page, they look at the web page, they get a sense of what it's about, but generally they leave that web page in less than 30 seconds and open another tab and check out the source. Who is the person who is behind this website? What does it say? And this, Sam Weinberg characterizes as a process of lateral reading. Now, the problem with students, and he shows this in his research, is they open the website and then they tend to read the website and try and evaluate it for themselves. And they can't do that because they don't have sufficient knowledge to do that. And then they get deluded by the carefully selected arguments that have been made in that way. So you have to learn that the first thing you do is check out who is behind this website. And you have to use authoritative sources, such as Wikipedia, Snopes, sourcewatch.org, and the web pages of scientific institutions to do this. I mean, sometimes you don't have to go very far to find out that there is a conflict of interest. And this takes us on really to what I would call the first check that you have to make. And this is this source of information credible? Because you need to ask, first of all, is there a conflict of interest? So one of the exercises we've got in the report is looking at a website called co2science.org. If you do lateral reading, check out who's behind it. First thing you find is it's funded by the oil industry. So that instantly says, you shouldn't really be believing this. It's not an independent source. There's a conflict of interest. But are there other evidence of ideological bias? To what extent is it politically neutral? That's pretty difficult these days for anybody to be that. But what are the signs of objectivity? And now, all of those, unless they pass those tests adequately for you, then you really should be thinking about rejecting this source. This is not a credible source. You can't use it authoritatively in that sense. But that then, if it does pass those tests, so you're happy enough with those tests and want to go further, the next question you have to ask is, does the source have the expertise to vouch for the claim? And this is more difficult because we don't teach about this in science. You know, what is it that enables somebody to claim to be a scientific expert? A nuclear physicist, for instance, is not an expert in climate change. And yet this is what has commonly been used by people who wish to undermine science. They know that people can't distinguish one scientist from another, so they recruit a scientist to support their particular view, even though they don't have expertise in the domain. This was a big issue at Stanford when a man called Scott Atlas was recruited by Donald Trump to advise him about policy on COVID-19, when he himself has no expertise. He's a scientist, but he has no expertise in virology. So somehow or other, you need exercises. This is not something to be taught in some kind of dry way. This is only going to be acquired by giving people opportunities to engage in evaluation and ask these kinds of questions. What track record do they have? What reputation amongst their peers? What credentials and experience? What institution do they work for? And again, if they don't have, the evidence is that they don't have expertise, then you should reject the source. If they do have expertise, that then takes you on to the third of these, which is the next one. So why is it important for us to address this? and why does science education have to do something about it? Well, first of all, science occupies the epistemic high ground. What do I mean about that? I'm not trying to claim some privileged position for science in that way. The fact is that many of these purveyors of misinformation try and present scientific evidence, and they present scientific evidence because they know that will be more convincing to people. And so, given that is a fact, then people need to understand what the nature of science that enables claims to be justified and not. Now, the problem is that many outsiders lack the knowledge to evaluate data and evidence for themselves. As I said, my example of climate change is one example. But if it came to the masks, okay, anything to do really with COVID, I don't have that kind of knowledge. So given the fact that my knowledge is bounded, I've actually then faced with making a judgment of trust. But what you need to know is that producing reliable knowledge is a core commitment of science. This is what the scientific enterprise is devoted to in a very big way and in quite a complex way. And it does it through a set of social practices. One particular piece of knowledge that you need to understand is the role and significance of consensus. Most of the science that we teach in school science is consensually agreed science, and it is the settled facts of that consensus. And science puts a premium on subjective agreement. That's what it's trying to do. Once it's achieved that, it moves on. And it does that through a set of social practices, peer review being one of them. But as in our discussions, the conception of peer review that I think vaguely appears in at least one curricula is a very narrow thing. Just because one article has been peer reviewed and published, that doesn't mean that this is an established, settled scientific fact. It means there is some good evidence for it, but it needs to be confirmed. And peer review is an ongoing process. There's pre-publications that get reviewed, there's funding that gets reviewed, people go to conferences where they present things, and only through that long ongoing process does a settled consensus emerge. One article itself is insufficient. And then obviously, as I pointed to, you need to know some of the criteria of scientific expertise if you're to make that judgment. Also, what you need, I think, and this is what we're arguing, is one of the challenges for school science is the fact that it deals in certain science means that it very rarely traffics in exercises that involve uncertainty. Now, I would hope that going forward, it's very easy to give kids data sets which do not produce straight lines, where there are issues to be resolved about outliers, where there are issues to be resolved about which measurements, how you produce a good measurement in that sense. And that's something that needs to be thought about. And then there is also, there's a distinction between cause and correlation, because a lot of these false arguments are based on mixing up cause and correlation. And also, I think what we've got to think about is teaching students, this is more general possibly than science, that actually as individuals, we are very flawed when it comes to reasoning. We all suffer from confirmation bias. We always pick out the evidence that supports our arguments and dismiss the evidence which doesn't. And this leads to errors in human reasoning. It also leads to errors in science in that kind of way. So these are, I think, some of the things that need to be addressed. If they were addressed, that then takes you on, I think, to the third element of our heuristic, which we're arguing for. And actually, we have a paper coming out of Science, I'm told, tomorrow with these kinds of arguments in it, which is there a consensus among the relevant scientific experts? Because consensus is important, and you need to understand that consensus is important. Now, if there is a consensus, then the general thing you would be advised to do is to accept the consensus. Now, this is a point at which some of the naysayers of science use the Galileo gambit. The Galileo gambit is basically to say, well, yeah, I may be outside the consensus, but so was Galileo, and he was right. And that's because Galileo was an exception. Okay, most naysayers against the consensus are not. And if there's no consensus, then you're well advised epistemically to say, well, what's the difference? I mean, some of the facts and arguments about masks, to some extent, are questionable. In what context, for how long, okay, how often do you change them, these kinds of things. So you have to probe the nature of the disagreement. This requires effort and work in that sense. And then you have to ask questions like, what do most highly regarded experts think in that way? So that is, I think, and all we're really suggesting is that students are introduced to these ideas through a set of exercises that they do regularly. And when they're doing the exercises, then they're more likely to be interested in the answer to the question of what makes somebody a scientific expert and what doesn't make somebody a scientific expert. It's not something you could stand up and teach at the front, I'm afraid, because that would kill it stone dead. This has to be done through practice. It's an acquired skill in that way. Also, I think what we're trying to argue for in the report is a sense of generating intellectual humility, that we people, I think, forget that a standard science education from K to 12 has about 1,500 to 2,000 hours. You can't possibly educate people in the whole body of knowledge. The approach to what knowledge we do educate, I think, is highly questionable. It tends to be, as I've argued before, foundational, starts with the bricks and hopes you see the edifice by the end, but most people leave before the end. Whereas I would much prefer to start with the building and say, isn't this wonderful? And then do a little bit of thinking, well, what are the bricks that support it? And I think it's in the quotation there below, which is knowledge. Knowledge is required to fit information into, make sense of the information. Because one piece of information alone is not very significant. It's its relationship to other things that make it significant and important. So it's important to know how an entity or concept is related to others, what its significance is, how it came to be, and why this knowledge can be trusted. Knowing what photosynthesis is, for instance, is of little value by itself. Being able to explain its significance, understand why it's such a crucial and important reaction, and how it's sustained is. Okay, and somehow it fits into the scheme of things. And that's, I think, is a concern which has to be addressed. So what do we see as being the implications of this, and how might they be addressed? Well, the basic implication is that science education has to provide a deeper understanding of the social practices of science that enable the production of reliable knowledge. And it is not doing that at the moment. If you're lucky, you get a little bit of the nature of science, but the nature of science doesn't talk about, for instance, peer review, significance of consensus, and how it functions as a community in order to ensure that error is minimized. You can never get rid of all error, and there is rarely fraud in science as well, but that's rare from that point of view. Digital media and information literacy has to be a core feature of every discipline. That's the work on click restraint and lateral reading in that way. And then it's clearly something that the next iteration of standards should attend to. But, and I think this is what we're trying to argue, it cannot wait. Because, I mean, this is a process that we are trying to put together at the moment. Somebody's given us some money to have a conference on NGSS 2.0. What we might do to improve it. But that's a long-term process. Getting a group of people together to rewrite the standards is something that happens every 2 decades if you're lucky. And so something has to be done about it now, because this is serious. And you're sending people out into the world without the competency to check or look critically about some of the things that are confronting them. And some of the things that we're talking about don't take much time. It's just a few exercises. Although we do talk to teachers, we present it to teachers, and they do like what we're doing. They, I mean, as a teacher of science, you're very concerned when you get somebody in your classroom questioning the science that you are teaching. And so they are very concerned to do something about this, but they obviously point to the fact that the standards are what they are. So we are recommending, obviously, that standards and curricula need to be revised. and we shall see what happens there. New curriculum materials are needed. Some of them have been produced already. We produced a few samples. Sam Weinberg has produced a few samples of exercises that you can do. Clearly, there's a program of professional development. I tend to regard that as being a kind of long shot. Simply, and why do we need a program of professional development? Well, most people who teach science and who have been practicing sciences themselves, they don't have an understanding of the social practices that enable the production of reliable knowledge. They don't have an understanding of the significance of the consensus. It's not something they have been taught themselves. So clearly it's something that needs to be explored through professional development, but that's a long-term issue. The easiest thing to do is to have new assessments where you ask students to identify flawed websites, flawed reasoning, and this is something that will be in the 2025 version of PISA. There's a new competency there to research, evaluate the credibility of information, and there will be assessments asking students to identify flaws. Well, I hope they will. I'm not writing the assessments, but I very much hope they will. I expect there to be in that way. So that, I think, is the kind of broad outline of what I have to say. I'm going to finish at that point. That is the report. As I said, it's available from that website. And I'm very happy to answer any questions that people might have.
Well, thank you so much, Jonathan, for this very engaging talk. I'm sure there are lots of questions. First of all, I'd like to thank you and applaud you for this wonderful presentation. And for those who haven't read the report, it's I think even more after today, you'll probably be very motivated to read it. I think it's not only very important report, it's also very well and clearly written. So thank you very much.